Hi, myself, Dr. S.K. Bushra, former HOD, Department of Physics, Cotton University. This is a video lecture in physics for class 12 students, and the topic is electrostatics. Lesson 3 of chapter 2 on electrostatics of conductors. In this lesson, we will consider basic properties of conductors and then a few problems with solutions. So let's begin. Electrostatics of conductors. We have already discussed about insulators and conductors. In insulators like wood, plastic, etc., each electron is attached to a particular atom and hence is incapable of participating in any kind of buck motion. In conductors, on the other hand, the valence electrons of the constituent atoms become the free electrons. The free electrons are not free enough to leave the conductor, but they move about randomly throughout the material. One may state that conductors contain almost an infinite supply of free electrons. In the light of above observations, let us discuss the basic properties of conductors. Number 1, electric field inside a conductor is zero. To know the reason, let us consider a conductor in an external electric field, E0. The external field causes electrostatic induction in the conductor. Induced opposite charges continue to pile up at the two ends of the conductor until the field E1 produced by them completely cancels out the original field. The whole process takes place almost instantaneously. Number 2, charge density is zero inside a conductor. The net charge is zero inside a charged conductor. This can be explained on the basis of Gauss's law. Let us consider an arbitrary volume bounded by an imaginary surface inside a charged conductor. The electric flux across the surface is zero because the electric field is zero inside the conductor. Therefore, as per Gauss's law, the net charge enclosed by the surface is zero. The volume element inside the conductor was arbitrarily chosen and could be made as small as possible. Therefore, the inference that the net charge is zero holds good for every point inside the charged conductor. Of course, there will be charges inside, but exactly as many positive charges as negative, so that net charge is zero. Number 3, any net charge resides on the outer surface of a charged conductor. We have seen that the net charge inside a charged conductor is zero. Therefore, only place available for the net charge to reside in a conductor is its outer surface. Regarding the asterisks, this can be established from energy consideration as well. Its authentication is left as an exercise for you. Number 4, just outside a charged conductor, the electric field is normal to the surface. Otherwise, charges will flow along the surface and will not have electrostatics with charged conductors. The normal component cannot impart motion to the charges as they are, that is, the charges are constrained to remain on the surface. Field is outward for positively charged conductors, while it is inwards for the negatively charged. Number 5, electric potential is constant throughout a charged conductor. Let A and B be two arbitrary points within or at the surface of a charged conductor. Then, with usual notations, V at B minus V at A is equal to minus integration A to B E dot dl. For interior points, E equal to 0, and so V at A is equal to V at B. For points at the surface, the field is normal to the surface, that is, E dot dl is equal to E dl cos 90 equal to 0, And so here also V at A is equal to V at B. Thus, a charged conductor is an equipotential space. Let us highlight this line. The value of the potential of a charged conductor is determined by the amount of charge present as well as by the shape and size of the conductor. For example, the potential of a charged conducting sphere is V equal to 1 by 4 pi epsilon naught Q by R, where Q and R are respectively the charge and radius of the conductor. The other quantities are standard. Number 6, electric field at the surface of a charged conductor. In the figure, a Gaussian surface in the form of a closed cylinder settles a charged conductor in a manner that a fraction of it lies inside the conductor. The cross-sectional area of the cylinder is made tiny enough so that the surface enclosed by it is essentially flat, and the surface charge density on it and the electric field just outside there are essentially constants. Let us start with a positively charged conductor. Let the cross-sectional area of the cylinder be A, and the charge density of the enclosed part of the surface of the conductor be sigma. The electric flux through the pillbox is integration over the closed pillbox E dot dA. We know that the field is 0 inside the conductor and the field is normal to the surface just outside the conductor. Let us highlight these 2 points. Hence, the inner lead will not contribute to the flux because E is 0. The curved surface of the pillbox too will not contribute because E dot dA equal to 0. The flux is contributed only by the outer lead of the pillbox, where the field is finite and normal to the lead. Therefore, the flux through the pillbox is, as given by equation 1, it is E multiplied by A, simple scalar multiplication. Now, the electric flux through the pillbox is given by Gauss's law as charge enclosed by epsilon naught is equal to sigma A by epsilon naught. This is equation 2. Equating equations 1 and 2, E multiplied by A is equal to sigma A divided by epsilon naught, which is E equal to sigma by epsilon naught. This is equation 3. Inserting the direction, electric field E equal to sigma by epsilon naught into n cap. This is equation 4, where n cap is a unit vector pointing away normally from the surface of the conductor. For a negatively charged conductor, n cap would have pointed normally towards the conductor. We know that in a charged conductor, the surface charge density is a variable quantity. It increases with the curvature of the surface. Therefore, the magnitude of the field just outside a charged conductor, too, varies with curvature of the surface. The field is stronger where curvature of the surface is sharper. Number 7, electrostatic shielding. Electrostatic shielding makes a region free from any outside electric field. A cavity inside a conductor is an electrostatically shielded region. No matter how much be the amount of charge in the conductor or how big an external electric field is, the cavity will always remain field-free. Examples of electrostatic shielding. Millikan's oil drop experiment. While measuring the charge of an electron, Millikan put the entire experimental setup inside a metal case so that no outside electric field could affect the internal content. You learn about Millikan's order of experiment later when you study atomic physics. Next example, Faraday case. A Faraday case or Faraday shield is an enclosure made of metal plates or metal wire mesh. The case effectively blocks any outside electric field. Next example, safety of a car. During thunderstorms, it is prudent to stay inside the car rather than in open space. The car's metal body acts as an electrostatic shield against lightning. Let us now begin our question answer session. First question is, find the electric potential due to a charged conducting spherical shell at a point outside the shell. We may find the required potential by evaluating the appropriate integral, where the symbols denote their usual meanings. But in this particular case, it will be prudent to exploit the already known electric field of the shell. Regarding the asterisks, we have been stressing it repeatedly that it is easier to handle in the potential than the field. But this and some other cases are special, wherein charge symmetry exists and Gauss's law evaluates the field rather easily. Let Q be the total charge on the shell and R be its radius. P is the point at the distance R from the center of the shell where small r is greater than capital R. Small r stands for the distance of the field point P from the center of the shell, whereas capital R stands for the radius of the shell. Gauss's law gives the field outside as 1 by 4 pi epsilon naught Q by R square into R cap. And the potential at P is minus integration infinity to R E dot dl. The displacement dl is dr dash R cap. Hence, potential at P is equal to minus 1 by 4 pi epsilon naught integration from infinity to R Q by R dash square dr dash into R cap dot R cap. And we know R cap dot R cap is equal to 1. So we get, after simplification, this. Then we carry out the integration. Then we put the values of the limits, lower and upper, and we get 1 by 4 pi epsilon naught Q by R as the potential at P. Here R is smaller, giving us the distance from the center of the shell to the field point P. This is the final result. Now, what is the potential on the surface of the shell? For this, we set the upper limit of the integration as capital R. We remember capital R is the radius of the shell. So potential at P is equal to minus integration infinity to R E dot dl. Here P is a point situated on the surface of the shell. Next, substituting for E and dl, we get, carrying out the integration and then inserting the limits, we finally get V at P as 1 by 4 pi epsilon naught Q by capital R. The result shows that the surface is an equipotential. What is the potential inside the surface of the shell? To find the potential inside, we break the integral into two parts. One, integration from infinity to R, that is to the surface. Then integration from capital R to small r, that is from the surface to the interior point. Here, small r is less than capital R. We have already defined what small r and capital R mean. The second integral is equal to 0 because electric field inside the shell is equal to 0. We concentrate on the first integral. Then finally we get potential at P, which is an interior point of the shell, is given by 1 by 4 pi epsilon naught Q by capital R. Thus, the potential is constant inside the shell and is equal to the potential at its surface. This is as it should be as per the electrostatics of conductors. Remark: for a charged conducting sphere, the conclusions are identical. I leave it as an exercise for you. Next question. Find the energy gain by an alpha particle when it is accelerated by a potential difference of 100 volts. The charge of an alpha particle, Q, is equal to 2 times E, where E is the magnitude of electron charge. Therefore, kinetic energy gained by the alpha particle is 2 into 1.6 into 10 to the power minus 19 into 100 equal to 3.2 into 10 to the power minus 17 joule. Or the same kinetic energy can be expressed as 2E multiplied by 100 equal to 200 electron volt. Next question. Taking the origin at the center of a charged spherical cell of radius 5 centimeter, draw the graph of the potential with distance, given the potential of the cell is 10 volt. The graph will be as shown in the figure. We have plotted distance along x-axis and potential along y-axis. We can see that up to a distance of 5 centimeter from the center of the cell, the potential is constant, is equal to 10 volts. Beyond 5 centimeter, potential falls as per the variation 1 by r, where r is the distance from the center of the spherical cell. This brings us to the end of the lesson 3 of chapter 2. We'll pick up capacitors and capacitance in the next lesson. Till then, goodbye and thank you.